The title of the colloquium today is The Revolution of Thin Film Transistors, and will be given by Dr. Elvira Fortunato. Dr. Elvira, she was born in Almada, 1964. Almada is on the other side of the Lisbon, it's a city on the other side of Lisbon. And she's married with Dr. Rodrigo Martins, so I mention it because he's here, her husband is here also. They have children, girl, 11 years old. And he's also a member of this group, Dr. Rodrigo Martins. Dr. Elvira is the director of the Cinemat I3M, which is a center of material research of the Faculty of Science and Technology of Lisbon's Universidade Nova. She got her basic education in science at that university, and in '85 she got her licentiate thesis and later on the PhD at the same university. Dr. Elvira Fortunato has more than 200 papers in international peer-reviewed journals, and has been invited to speak at many international conferences during the last 4 years. In 2006, for instance, she was organizing the first international symposium on transparent electronics in France. Her laboratory has 12 registered patents. 3 of them are international, 1 of them is with the multinational company Samsung. She got several awards. First prize in 2005 is an award of Incentive for Scientific Excellence from the Ministry of Science and Technology in Portugal. At February 2008, her laboratory started developing the 3rd generation of solar cells in contract with the Japanese multinational Fuji. At May 2008, Samsung presented at Los Angeles a new generation of display for mobile phones and other electronic devices, which is a result of the cooperation investigation at this laboratory. So I should also mention that at 21st July, the news on the fabrication of the paper transistor was spread around the world. Financial Times, the electronic edition, put it on the web, and 3 days later there were more than 4 million hits in the Google search in all possible languages, including Russian and Chinese. But it was for her research on transparent electronics that she got, some days later, the 23rd July 2008, the most important award of the European Research Council in the area of engineering sciences. It was the first time that the European Research Council had that prize, and she got the first position. Dr. Elvira Fortunato is ranked internationally at the top 5 in her area of research. So we are happy that she had time to come to Stockholm and to Albanova to tell us something about her ongoing research. Please, Dr. Elvira.
Thank you very much, Dr. Antonio Pereira. First of all, I would like to thank you the invitation and to invite me to Albanova and to talk a little bit about transparent electronics and the revolution or evolution of the thin film transistors. Of course, this is for me a privilege and also an honor and a responsibility to give you a talk in this so good and excellent scientific place. Okay, my name is Elvira Fortunato. I work at New University of Lisbon, and I am associate professor at the Material Science Department. So my background is material science. First of all, where we are, Dr. Antonio explained a little bit, but maybe for those doesn't know where is Portugal, or more precisely, we are here, the west part of Europe. Now we are here at this place. Only 4 hours, not too much. And Lisbon is over there. is the capital of Portugal, and my faculty is on the other side. So this is the river Tagus, the ocean, and our faculty, our campus, is near the beach. In fact, we have 20 kilometers of white sand beach. This is Costa da Caparica, and the beaches are, and the pages, the food, everything is very beautiful. This is a picture of our campus, Campus de Caparica. So we have, this is Lisbon over there, the Tagus River, the ocean is around this place, and this is our campus. We have more or less 60 hectares, and our department, our laboratories are located in 3 main buildings. Here, this part of the buildings that belongs to Material Science Department, and we have laboratories on these research centers nearby. So, and we have all the chemistry, environment, mathematics, physics, civil, all the other departments. Okay, I will start with a briefly introduction to the history, or I will try to explain you a little bit the history of thin film transistors, or field effect, if you want, the field effect invention. And this is, the history is very beautiful because the field effect was invented and patented in around 30. But more or less 30 years later, before the production of the first working field effect transistor. This was done more or less in the same period, in the same time, by 2 persons, two scientists, one Oskar Hale in Germany, the other one Julius Lilienfeld at United States, and they patented the idea of a device where we can control or we can modulate the conductivity of a semiconductor by using an external perpendicular field. This was a dream, in fact the dream of Lilienfeld, and in fact this is the field effect. So the invention of the field effect was proposed and patented around the 30. So in fact what the field effect means is the capacity to modulate the conductance of a semiconductor through a perpendicular electric field. But of course, at that time, it was impossible to perform this type of device because the materials and the technologies were not available. They realize in the patent we can read the thicknesses for the semiconductors are exactly the thicknesses that we are using today in the well-known TFTs. So the thickness for the semiconductors are several hundreds of nanometers. But at that time, of course, it was impossible to realize and to perform experimentally the device, to fabricate the devices. Only around 30 years later, it was the first demonstration of a working field effect transistor, or a thin film transistor. This was done by Professor Weimer at the RCA laboratory at United States. This is the typical output characteristics of this TFT. He evaporates, he uses a very simple system, a classical evaporation technique. He deposits cadmium sulfide on glass. For example, a typical semiconductor used for photodetectors. And the mobility he achieved was very good, around 200 square centimeters per volt per second. Just to make a comparison, because, for example, the TFTs that we are using in our laptops or in every display that uses an active matrix, the TFTs are made on amorphosilicon, and then the electrical mobility is around 1. But at that time, they achieved already 200. But this period was a very important period because it appears also the first MOSFET. So the first MOSFET, and with all the capabilities to make integrated circuits, and for the microelectronic industry, the thin film transistors were left a little bit behind because due to the importance of this new type of semiconductors and devices. Only around the 70s, and also because more or less during this period it appears the liquid crystals, and also due to the need to use larger displays, and also due to the possibility or the proven that done by Professor Lecomber and Professor Spear at Dundee University in Scotland, they show that it is possible to dope a morphosilicon, and they can use a morphosilicon as a true semiconductor. And for example here, and they produce the first morphosilicon TFTs. This is a typical transfer characteristics of amorphosilicon TFTs, where you can see that the on-off ratio is very high. We can switch the device from an off state with 10 to minus 13 amps to more or less minus some tens of microamps on the on state. The swing voltage is very good, and also the turn-on voltage is very low. And also with the invention of a morphosilicon, if you want, and with the possibility to grow this material, to deposit this material on large surfaces at low temperature, all this technology revolutionizes all the display industry. And if, for example, even today, all the displays that we are using are based on a morphosilicon TFTs. The TFTs inside this screen. This is an image, a picture with 4 pixels, and here is the TFT that switch the pixel of the display. Of course, the devices work well, even we are still using this type of transistors in our displays, but the material presents a drawback. The mobility is quite low, so it's around 1 square centimeter per volt per second. In order to improve the performances of this type of TFTs, one of the ideas that appeared around the 80s was to crystallize a morphosilicon. For example, if you are using, for example, laser, we can increase the grain size. In this graphic, what we have, the green dots are the grain size, and the orange curve is the TFT mobility. And as the grain size increases, we can also observe an increase on the TFT mobility, and we can achieve values around 400 square centimeter per volt per second. So we can increase a lot the mobility of the device, or if you want, the electrical performances of the TFTs. Nevertheless, for making large areas of displays, usually the uniformity of these TFTs or of these polycrystalline material is not good. If you are looking for large areas, you have some non-uniformity, and the devices are not working properly. So this is not, for small areas maybe it is an advantage, but if you are looking for large areas, this is not the best choice. So, around the 19th, and also it appears a new family of materials or semiconductors, the organic semiconductors. And for example here, this is one of the first TFTs using a semiconductor Pintasen, an organic semiconductor. Usually this type of TFTs, they are P-type. Here the output characteristics, the transfer characteristics, and they work quite well. So nowadays organic semiconductors are quite attractive because we can produce these materials at low temperature. Also the cost associated is not high, so they present a low cost. And also we can deposit this type of materials on flexible, on plastic substrates. These are the main advantages of organic materials. Even today we have around the world a lot of conferences about plastic electronics, a lot of conferences and investigation on this topic. Nevertheless, the mobility associated with this type of transistors is similar to that one of a morphosilicon, so the improvement is not so good, so it's not so high. And also we are still looking, we have some problems related to the stability of organic devices. Usually they are not so stable as the inorganic devices. So, and more recently in these, after 2000, it appears, for example, it was proposed by Professor Ozono at the TIT laboratories in Japan, a device where we can use an oxide semiconductor as a semiconductor. So we can substitute the semiconductor, the traditional semiconductor, by an oxide material. In this report, he uses a monocrystalline complex oxide with indium, gallium and zinc, but the temperatures for growing this monocrystalline film was around 900 degrees. So if you are looking for this, to use this type of devices, for example, for large panels or for the industry, this is also a problem. So in the same year, Professor Wager at Oregon State University present the same concept, but by using for the channel layer zinc oxide. He produces the material by sputtering, but also he needs to heat the material or the device up to 600 degrees, which, for example, if we are looking for plastic substance, this is a limitation because we cannot heat a normal or a cheap polymer at 600 degrees. So 1 year later, we propose more or less the same. We use as the channel layer zinc oxide, but we grow this film at room temperature. So we produce for the first time in the world a fully transparent TFT at room temperature. So, and we are very happy because more or less two weeks ago we are preparing a book and a chapter for another book, and I was searching for TFTs, and I found at Wikipedia a report that a Portuguese laboratory also performed, not only for the transparency but also for the paper transistor that we produced the first time in the world. So we are very proud of our research. So this is just a comparison between a MOSFET and a TFT. They are quite different in production, but very identical in the way how they work. For example, here I have a cross-section of a MOSFET N-type, and the TFT also N-type. So for the MOSFET, what we have the silicon wafer. We need, for example, the silicon wafer must be P-type. We diffuse the source and drain with heavily N plus layers. We have the dielectric layer and the metal gate. Of course, here for the TFT, we need to have a substrate. We deposit the semiconductor, also depending if we are using a bottom or a top gate, the semiconductor, the dielectric layer, and also the gate. In this type, we have a top gate configuration. The substrate could be a glass, a polymer, or even paper, whatever you want. So, concerning the way how they work, so the MOSFET works in the inversion region, while the TFT works in the accumulation regime. Of course, for the MOSFET, the off, and of course, if you remember, the TFT or a MOSFET are like a switch. What we want is to have a very high on-off ratio, so the off state, the current associated to the off state should be as low as possible, and the current associated to the on state should be as high as possible. So in order to guarantee a very low current for the MOSFET, the off region, we should have these PN junctions, just to avoid to be able to have a very low current. In the case of the TFT, since the resistivity of our semiconductor is much higher than the resistivity of the silicon wafer, the silicium, we don't need to have this type of diodes here. So the principle, the production is easier than the case of the MOSFET. And of course, the thicknesses of the two materials are quite different. Here, of course, we are limited to the thickness of the wafer we are using, and here we are limited to the thickness. The thickness of the semiconductor by itself is around 1 micrometer, or even in some cases much lower than 1 micrometer. The semiconductor layers, here all these belongs to the semiconductor materials. So, why today we are looking for amorphous oxide semiconductors, and why this type of materials, amorphous oxide semiconductors, are interesting for thin film transistor applications. Because they combine simultaneously the advantages of amorphous silicon and polycrystalline silicon TFT. So we can combine the two main advantages of amorphous silicon, amorphous silicon and polycrystalline silicon in one material. First, we can deposit the material at low temperature or even at room temperature. So we are able to use, we are not limited to the substrate that we want to use. And since the material is amorphous, the surfaces are very smooth, which is typical for amorphous materials, so we don't have grain boundaries. For processing, this is a very good advantage, because if I'm making 1 meter or 2 meters, I'm processing large areas, it is better to have amorphous materials because they are more homogeneous. If I'm making a lot of microelectronic processes, etching and so on, I don't have grain boundaries. So the integration on large areas is much easier. So these are some examples, some prototypes that appeared 2 years ago from Koshi in Japan and ETRI in Korea. So they present some prototypes using for the active matrix TFTs based on zinc oxide. So, okay, this is a picture. The display doesn't work quite well. We have some defects, but it's working. So even the diagonal is not too high, 1.46 inches, and this was based on LCD, and this one was based on OLED technology, but both used zinc oxide TFTs. And we are not limited to displays, we are not limited to thin film transistors. We can also use this type of materials, this type of new oxide materials for integrated circuits. For example, in 2006, the group from Professor Wager present a 5-stage ring oscillator using indium gallium oxide TFTs. And also Canon present last year at Strasbourg a 11-stage ring oscillator using amorphous gallium indium zinc oxide TFTs. And more recently, TOPAN, because now e-ink, this type of electrophoretic displays are very used, because the production is the cost associated with the production of this type of display is very low. They present a display using the e-ink technology, using also amorphous gallium indium zinc oxide TFTs. And this display has 4 inches. And also LG presents a display using the same type of TFTs based on these amorphous gallium indium zinc oxide, a display with 3.5 inches diagonal using OLED technology, a more expensive technology. And this year it was presented by the first time by Samsung at the SID conference, the biggest display conference in the United States. 2 prototypes, one based on OLED, the other one based on LCD technology, with 2.1 and 15 inches, both of them using indium gallium zinc oxide TFTs. And also, we can also use other technologies instead of all the main technologies associated with the production of these type of materials and devices are based on sputtering, but also we can use other techniques, like for example inkjet. This was presented by HP some years ago, where they inkjet all the materials, and they perform a TFT based on zinc oxide, but using a very, not a normal, but a very similar inkjet printer. They substitute the inks from the appropriate solutions, and we can deposit all the materials. And since we are not using lithography, this is an additive process, the cost is quite low. Of course, the results are not so good, but these results, they presented these 5 years ago, so I believe now they improve a lot. But the first results are 0.3 square centimeter per volt per second for the mobility, the on-off not too high, 10 to 5, and the V-on quite high, high in absolute value, 8 volts. They work in depletion mode. So, but this is good. So, why metal oxide conductors and semiconductors? Because this is very easy and very nice, very beautiful, because we can, by changing the deposition conditions, we can have the same material as a conductor or as a semiconductor. So the main materials is the same, but since we can modify something related, for example, with the amount of oxygen inside the structure, we can have a conductor or a semiconductor. For example, and you know that metal oxide thin films are playing an important role in many applications due to the wide range of properties. And this is not possible with other materials, only with oxide, or in this particular case, metal oxide films. We can use these oxide or metal oxides on optical, mechanical, electrical, chemical, structural applications, a lot of them. Concerning the applications for optical coatings, we can use these oxides on optical filters, anti-reflection coatings, on piezoelectric devices, also gate dielectrics, for example, for high-key dielectrics, diffusion barriers, for example, if you want to protect some special containers with alumina or silica, on electrochromic windows, for example, tungsten oxide is well known, on gas sensors, and also on TCOs and TFTs. What is the meaning of TCOs? Is transparent conducting oxides. Maybe the most known is ITO, is indium tin oxide, is well known and is used as a transparent conductor. But these two types of materials, or two types of families, are related to what we call transparent electronics. If you want to make something that is transparent, if we want to perform a device or an integrated circuit with oxide semiconductors or transparent, we need to have oxides that are conductors and oxides that are semiconductors. If you succeed to have these two types of materials, of course, we will succeed to have devices and integrated circuits. So, these materials are quite old. The first transparent conductor was done more or less 100 years ago by Baedeker, and it was cadmium oxide. Of course, for this type of materials, what we want to have a high transmittance and simultaneously a low resistivity. That's the characteristics or the properties we want for a transparent conducting oxide. Today, most of the TCOs of this type of oxides are based on this system: indium oxide, tin oxide, and zinc oxide. The ITO is between indium oxide and tin oxide. But since indium is expensive, we are looking today for other materials, and especially zinc oxide works very well and is a good alternative to indium oxide. So of course, what we want is to have, our target is to have a high conductivity or a low resistivity, and of course a high mobility and or a high carrier concentration, because you know that the conductivity is N plus multiplied by the mobility. For example, here, this is a typical graphic from, for example, this is for silicon. This is very well known. For example, here we present the mobility as a function of the impurity concentration. And what happens is that if you increase the carrier concentration, the doping, if we increase the doping, what happens to the mobility? It starts to decrease. And for high levels of doping, around 10 to 19, the mobility, the electron mobility is around 90 square centimeter per volt per second. And for example, we can perform TCOs or oxide semiconductors with very high values of mobility, around 60, and with a high carrier concentration. But we can perform this type of materials at room temperature. So this is a very huge advantage for this type of oxides. So here, for example, even if we compare this type of materials with silicon, and this is monocrystalline silicon, this is the typical graphic that we use for microelectronics to calculate the resistivity as a function of the doping or the impurity concentration. And we achieved these values, for example, for amorphous indium zinc oxide fields. Concerning the materials that are already tested for TFTs, of course, and this is around all the world, the first publications used more simple systems like zinc oxide, tin oxide, and indium oxide, and due to some instability of the devices, now we change, and there are other approaches using what we call multi-component oxides. Usually it's better to work with multi-component oxides because we can control better the stability of the materials. If we are using these binary oxides, the stability is not so good. And of course, if we compare this, the left part are the materials and even others, the right part are the technologies. We can produce all these materials or the devices based on these materials by several techniques. Expensive ones, PLD, spudging, or even salt shell, solution-based, or even inkjet. So we can have the window is very, very large. And in some cases at room temperature, not all, but in some cases, using some type of technologies, we can produce all these materials with with good electrical properties and optical at room temperature. And, for example, this is a comparison because we are dealing with other semiconductors. For example, this is for what we call conventional semiconductors. This is for the case of silicon, what we can see from this table. For example, if we want to have high mobility, for example, if we want to reach high mobility, of course, the grain size, we should increase the grain size until the monocrystal. And of course, to achieve this, look about the temperatures. The temperature associated is also high. So this is like that. If I want to have a material, if I'm using silicon or a conventional covalent semiconductor, in order to have a high mobility, of course, the grain, I should increase the grain, and also the temperature associated should be higher. And these type of oxides are completely different because, as you remember, we can achieve high values of mobility at room temperature, and the materials are amorphous. So the amorphous structure of the material is not a limitation for the electrical performances of the same material. Why? Because we are facing a new type of semiconductors. In this case, we are not talking about covalent semiconductors, but we have ionic semiconductors. And for example, here we have a comparison between amorphous silicon and these amorphous oxide semiconductors. This is the metal orbitals, s orbitals, and what we have here, we have disorder, like here, the material, both materials present a disorder structure, but here we have some overlapping of the orbitals, and we have a path, a conduction path for the electron. So in this case, the disorder do not limit the electrical, for example, the mobility of the material, because the way the conduction mechanism is different from the conventional covalent semiconductors. And that's why we have for an amorphous structure with an amorphous semiconductor a so high value of mobility. If you compare with amorphous silicon, the mobility is 1, and we can achieve mobilities around 60, 50, even at room temperature. And of course, this is because we are talking with a new class of semiconductors. Polite, not polite, depends. Okay? So, now I will present some results on the devices that we have produced in the results that I will show now are results from our laboratory. And I will present results briefly on IZO, this system, GIZO. This is indium zinc oxide, gallium indium zinc oxide, and gallium tin zinc oxide, because also we replace indium by tin because, due to the cost of indium. So this is a schematic view of our clean rooms. We have 2 clean rooms. We have several deposition systems, PCVD for amorphous silicon. Also, we work on amorphous silicon. Several sputtering machines. In fact, I saw today one similar to that one from Asia, from United States. You have at your nano lab fabrication a similar sputtering used for spintronics. We use this equipment for oxide semiconductors, mainly at this moment for dielectric materials. Again, also the microelectronic, the yellow room with the mask aligner, and we have all the process for making not only the materials but devices and the characterization facilities for materials and devices. This is a deep look of the systems used. The new mask aligner we have, the yellow part, and several sputtering units. This is the new one. So, we perform everything at room temperature. This is an example of film, indium zinc oxide film deposit on silicon oxide on a wafer, and this is a TEM cross section, high resolution TEM image where you cannot see any crystals. So the structure of the material is amorphous. And this is the film deposit on a plastic substrate, just to show that it's possible to do this at room temperature. We perform some thermal tests just to see the stability. And even, for example, the material as produced at room temperature is amorphous, but even at 500 degrees, the structure is the same, is an amorphous. And this is the resistivity measured on air and in vacuum, and also is the same depending on the temperature. This means that the material is quite stable. Concerning the devices based on amorphous indium zinc oxide, and this is very interesting because, as I told you, we are using the same material for different applications, for TCOs or for semiconductors. For example, here is the structure, a typical structure of for a TFT with the IZO as the channel layer, and for source and drain we are using not the same but also IZO. So this is the substrate, the bottom gate, ITO, the dielectric layer, ATO. This is a multi-layer structure with alumina and tantalum oxide. And for the channel, for the semiconductor and for the source and drain, we are using both IZO. So what is the difference? Because for the drain and source, I need to have a material with a high conductivity. For the channel, of course, I cannot use a TCO. I cannot use for the channel layer a semiconductor with a high conductivity, otherwise I cannot modulate the conductance of the channel. That's the principle. I cannot have field effect. So, what is the difference? Is exactly the conductivity. For the channel layer, the amount of oxygen is higher than the case for the drain and source. So I use the same sputtering machine, but I change the amount of oxygen during the deposition. So for the channel layer, I need to have a higher resistivity, so the amount of oxygen is higher. For the source and drain, the amount of oxygen is lower. So the film, the conductivity is higher. But this is very interesting because I can use the same target and I play with the deposition conditions, and of course the oxygen is crucial.
Are you doing RF sputtering?
RF.
RF, and you bleed oxygen into the chamber?
Yes. Yes, I didn't explain that it's RF. We don't use for all these experiments DC, only RF sputtering. And this is a typical transfer characteristics. This is the off state and the on state. The currents we got are very high. So the first time we send these papers to the referees, they ask us if we make a mistake. And here is not, it cannot be milliamps, but usually is microamps. But no, it's that. We achieved very high values of current for the on state, of the order of milliamps. And even this is not the best device. In some cases we are 10 to minus 12, 10 to minus 13. But of course this depends not only on the semiconductor that we are using, but on the dielectric layer and also the interface between the dielectric and the semiconductor. Because for a device this is a little more complicated, and of course the interfaces are playing a crucial role. Just for you to have an idea, the thickness of this material, the semiconductor, is around 10-20 nanometers, which is very, very low. This is, I didn't mention, but for example, we obtain mobilities of the order of higher than 30. And these are typical output characteristics where you can see a very nice hard saturation. So all the curves are parallel, no leakage. So very, very nice. And here, this is a picture of, this is a graphic with the transmittance as a function of the wavelength. And as you can see on the visible region, the transmittance, including the substrate, is around 80%. And this is a piece of glass with 2.5 by 2.5 centimeters with several TFTs over there. Of course we cannot see them, but they are there. But the transmittance of the full device is around 80%. So also we have performed other TFTs based on another system, gallium, indium, zinc oxide, because why do we use gallium? Why we add the gallium to the system and not only to use, instead of using IZO, indium zinc alone? It's because for IZO it's difficult to control the carrier concentration. It's because it's very hard to control the number of carriers. And we use gallium just to lower a little bit the conductivity of the material, and in this way it's more easy to control the carrier, the concentration carriers. But again, the material is amorphous. This is a typical diffractogram of GIZO film, and the thickness over there is much higher than the thickness used on the TFT. This is around 300 nanometers. This is a TEM image where we cannot detect crystals. And since we are using 3 oxides, gallium oxide, indium oxide, zinc oxide, this is more complicated to see and to map all the possibilities and all the concentrations. And we are producing at this moment TFTs with these concentrations. And the typical structure, because of course we are talking about transparent electronics, but maybe for display industry the transparency is not critical, is not crucial. Why Samsung and all these companies that are making the displays are looking for this type of materials? Because the performances are much better. The cost associated is much lower than amorphous silicon, because even today for making this type of displays using amorphous silicon, they need to have the sputtering machines for the ITO, for the transparent electrode, and the PCVD machines for the deposition of amorphous silicon. By using this new technology, they only need to have sputtering machines. They don't need to use silence, diaphragms, all these dangerous gases. So, in some cases, it's not transparent. It's transparent because it is, but for them, the devices are, the performance is much better. And since we are studying different materials, for us it is better to use a standard or a test structure. And the easier is to use the typical silicon wafer with the well-known silicon oxide, because we know very well how silicon oxide works, is a good dielectric, and we can test in this type of structure all the semiconductors that we are producing here. That's why this is not transparent. But of course, after optimizing the material, you can perform the same using the bottom gate and the dielectric also transparent. And here are the typical thicknesses for the materials. And also for, just to avoid, we can use for the certain grain oxides, like in the case of IZO, but here we use metal, titanium, gold. Here are a summary of some TFTs that we performed using different compositions, using different targets, and the typical, what is important for a TFT is the mobility, on-off ratio, the V-on, the threshold voltage, and also the swing voltage that is important and is associated with the type of interface between the semiconductor and the dielectric layer. But as you see, you can achieve easily mobilities around 50 with a high on-off ratio, a V-on very low, -1 or 0, around the threshold voltage around 1, and also with a very low swing voltage. And we perform also stability measurements, because this is critical for the display industry. The devices should work. First of all, they should work. Secondly, they should be stable. We perform some stress analysis, and even, for example, after 100 hours, the shift associated with the threshold voltage was around 0.36 volts, which is very low. So this is much better than, for example, amorphous silicon. This is an image of one of our first active matrices produced in our laboratory. This is the typical configuration, the pixel area and the TFT. And this is a zoom of the TFT that we are producing. More recently, and also due to the cost of indium, we observed that the mobility, and this is hard, what we observed is that if we are looking for a TFT with a high mobility, it's important to have indium. So even if we replace indium, this is critical. And the amount of indium should be always higher than 40%. But we are looking for alternatives, and also the cost. Every know that the availability of indium is limited, and we substitute in our system the indium by tin, and the results are good. For example, here the material are still amorphous. This is the typical diffractogram of gallium tin zinc oxide film produced at room temperature and annealed at 300 degrees. The structure is amorphous. This is a SEM image, a SEM cross section, and this is a AFM topography. And these are the results for the devices. Of course, the mobility is a little bit lower, so we can achieve the mobilities of the order of 20, not so high as with the GIZO system, but they work properly, and maybe with some improvement we can also achieve higher values. And more recently, and just to finish the talk, since we are working at room temperature, so we are not limited with the type of substrate we are using, we think to substitute our dielectric film, our silicon oxide or aluminum oxide, with a simple sheet of paper. because you know paper is insulating, and what we did is instead of growing all the layers and produce the device with a substrate configuration, layer by layer, we make this to what we call an interstrate structure, because it's not a substrate, it's not a superstrate structure, it's an interstrate structure, because we start the device from the middle, from the dielectric layer. In one side we cover with the gate, on the other side we cover the sheet of paper with the semiconductor and the source and drain. And we achieved here, this is the configuration of the device. We use for gate electrode IZO, amorphous indium zinc oxide. This is the sheet of paper, the GIZO semiconductor, and the source and drain. And these are the results for two typical TFTs, or FETs, because this is an hybrid, it's not a TFT in the sense of the word. By using, for example, two types of papers, we can achieve nice curves. This is the transfer characteristics, and also with a very high value of mobility. Of course, this is a comparison between these two TFT, two hybrid FETs, and a standard one, the reference one. Of course, what is substantially different is the on-off ratio, because here we have some leakage. So the paper, of course, is insulating, but we have some leaks. And the on-off ratio is not so high, it's around 10 to third and 10 to 4. But also the mobility is quite high. We achieved very nice values for the mobility, and the devices work quite well, using a conventional sheet of paper. So, what we think about, and this is completely new, so we are now discussing and study a lot. We have a lot of open questions about this subject. But since the structure, and this is performed on scale, this is the same image of the surface of a paper. What we have here are the fibers, the cellulose fibers, and the porosity is too high. The roughness of the paper that we are using is very high. If we touch, it's smooth, but if we look this with, for example, an AFM, the surface roughness is around between 6 and 8 micrometers. And the semiconductor that is there, but we cannot see, the thickness is around 30 nanometers. We are depositing a thin film with 30 nanometers on a surface with a roughness of 6 micrometers, several orders of magnitude. So what we think is that since the fibers are aleatory, are random, we believe that we have some paths, and we have, this is done at scale. For the paper transistors it's impossible. For example, for conventional paper, to perform lithography, we cannot dip in the solutions a sheet of paper. We use for this type of transistors shadow masks. And for example, this is the source and drain. This is the scale. This is the channel length, the dimension of our shadow masks, 216 micrometers. And since we have this type of fibers, and we believe that we have some preferential paths, ways, for the carrier of the electrons. And that's why we achieved on this type of structure a so high value of the mobility. That's one of the explanations that we have at this moment, because otherwise it's hard to explain why the mobility is so high in this type of structures. Because the scale here is micrometers, but the material is covering all these fibers. So the fibers are covered with the material that we are depositing by sputtering. So, as general conclusions, what we can say that, of course, by using an amorphous structure is better because we can have large area uniformity. The devices present superior performance, especially the mobility is quite high. They are transparent. In some cases, this could be good or not, depends on the type of applications we are looking for. They are stable, also concerning electrical stability. They are able to be passivated because this is important in some cases, and since we are working with oxides, in some cases when we are depositing something or when we are passivating the material, the properties are different, and this is a problem because we are making a device, but after passivation it works in a different way. And we developed a technique, and we have now a patent with Samsung related with this specific issue. And also the structure is simple because we don't need to use the N+ contacts as the case of the MOSFETs or as the case of the amorphous silicon TFTs. The amorphous silicon TFTs, they need to have an N+ contact. So this is what we are looking for, is the ideal oxide material for TFT application. This material should have a high carrier mobility, a low carrier concentration, a non-vacuum deposition, if possible, and also low temperature deposition. So this is our ideal semiconductor. Concerning the applications of this technology, we have a lot. The pink ones are already implemented, so this type of applications for displays are already implemented, but also we have all these other possibilities. And if we perform a comparison between the conventional technology, but mainly for displays, with the amorphous silicon or these oxide electronics, what we can say? Concerning stability, amorphous silicon is poor, oxide is good. The TFT channel mobility for amorphous silicon is lower or equal to 1, and no way to increase this value. Here we can play. In some cases we achieved mobilities of the order of 100, so we are 2 orders of magnitude higher than for the case of amorphous silicon. The TFT functionality for amorphous silicon is a voltage control switch. Here we have diverse electronics application space. We have a wider view, other possibilities. And also, of course, this is what they call a multi-billionaire market. Of course, for amorphous silicon is more or less known, but for oxides, maybe due to the wider applications for this type of materials and technology, we can obtain in the future much higher market, if you want. And of course, I would like to thank to the team. This is not, of course, this is, as you know, this is a work of a very hard and motivated around 30 persons that work in our group. They are not all here. And of course, we need the persons, and they play a crucial role in the work, but also we need the financial support, either from Europe, from national agencies, and also from several companies, because today, due to all this success, we have a lot of contacts with industry, and this is the way why you can keep with us 30%, and also the type of infrastructure and laboratories I show you briefly. And thank you for your attention. And I'm open to questions or comments.
Please, questions. Yes? Hans, please.
You mentioned e-ink, this electronic ink.
Yes.
Could you explain a little bit about that? Is that the future display, and does that come into what you are doing?
Depends. It's very cheap. For making the e-ink are small drops of a special ink, and it's similar to liquid crystals. You can change the polarity of this ink, and we can turn the color to white to dark. It's very simple. But the construction of a display using e-ink is just to stick this foil on your active matrix. So the cost is much, much lower than, for example, if you compare with liquid crystal displays. To make a display like that is so difficult. Okay, it depends, but it's costly. E-ink maybe for some applications could be a solution. The resolution is not so high at this moment because you are limited to the size of these drops. But if you are looking for low-cost applications, this could be a solution. But for example, if you are looking for brightness, OLED technology is much better because even is much better than LCD because you don't need to have the filters. For e-ink, since you have only white dark, white black, you need to have filters to have RGB monitors.
So you cannot do it in color intrinsically? That's what you're saying.
Intrinsically, no. At this moment, no. But I'm not from ink. Even is another story. It's very easy to use, in fact. But for color and even brightness, contrast is not so good as the conventional OLED, for example.
You mentioned a ring oscillator, but most of your discussion of applications around displays, and I thought ring oscillators were very interesting to figure out the intrinsic speed of some kind of transistor. And is there other areas of application where the thin film transistors might be interesting, or are they too slow compared to MOSFETs, for example, for logic or?
Yes, but also depends if you can. I presented the ring oscillators because just to show that with this type of TFTs we can do integrated circuits. We can increase the complexity of a circuit. But for example, of course, the performance of these ring oscillators is not so good as the typical silicon microelectronic industry, but since they can be transparent or deposited on plastic surface, you can use them in other applications where it's forbidden for silicon. This is always, you see, this is a balance. With this type of technology, of course, my idea is not to make a microprocessor with this type of oxides. We can do it, but the results are worse. But in some other applications that are already forbidden for silicon, we have other things, and we can compete there because with the other is impossible. And also, since these things are new, even for us sometimes it's difficult to imagine other things, other applications, because this is new. Because now we will see a lot of things coming out.
I think that you answered also my question. I was wondering about the impact of this, the impact on the societal impact on coming technologies, these applications. But
okay, the most direct for now is display industry, by sure. At this moment, with the short delay is the display industry. But of course, this is open. This opens other applications.
any more questions? Then I think we will close the colloquium, and I thank again Dr. Elvira Fortunato for coming here.